Hey everyone, back to a new awesome video, and today we're going to continue with our electricity and magnetism series. Today we're going to keep exploring these DC circuits, and we're going to start treating the elements on their own and finding, for example, at the start the voltage change through both batteries and resistors. Then we will analyze a multi-loop circuit, and finally we'll see how we can join together different elements like resistors both in series and in parallel. So let's start. Great. Now we're going to explore how the voltage changes across these different situations. We have batteries going with the circulation direction in both directions and resistors, in which what's important is not the resistance on itself, but the circulation direction with respect to the direction of current that we have chosen. In this case, we have that this goes from, and of course, we have that in here, the voltage is going to be higher, as that's the positive side, than in here, which is the negative side. Therefore, the voltage is decreasing, which means that the change in voltage is minus epsilon. Now, in this situation, we have that the voltage is going from lower to higher. Therefore, the change in voltage is going to be equal to plus epsilon. Then we have these situations. And in here, we remember that the change in voltage through a resistance is related to the current by this constant R. Therefore, the magnitude of the change is going to be I times R. However, we don't know the sign. For that, we need to analyze our situation. We see that in this case, we're going from higher to lower. Therefore, the change in potential is going to be negative. However, in this other case, we're going from lower to higher. It's opposed in the current direction. Therefore, the change in voltage is going to be positive. And this summarizes the change in voltage across these single elements once they are isolated from the entire circuit. Alright, now let's examine this multi-loop circuit. As we said in the last episode, we need to first establish the direction of current. We're going to establish this one to go in this direction, I1, this one to go in this direction, I3, and this over here, I2. Then we also need to establish the circulation directions for each of our loops. We're going to take this one and this one. Now we start by applying the first Kirchhoff law, which says that at the junctions we're going to have that the currents going in equals the currents going out. So in this case we're going to have I1 equals I2 plus I3. If we see in the other junction we would get the same thing, I2 plus I3 equals I1. Now we apply the second Kirchhoff law and we'll start by this loop. So we're going from negative to positive, therefore we're going to have an E1 adding. Then we're going to have, as we're going in the same direction as current, a minus I1 R1. Once again, a minus I2 R2. And this is going to be equal to 0 as we're going all around the loop. Now we're going to take this one and we're going to start from here, as this is the positive part of it. So we would have going against the current, therefore it's positive, I2 R2. Then we're gonna put the plus epsilon 2, we're gonna write it over here, and then minus I3R3, because current goes over here and circulation direction shares the same direction. And all of this is gonna be equal to 0. And now you may wonder, what if we take this big loop as we could physically move this cable, take it, put it over here, and then this would be on the inside. So there's a closed loop over there. However, if you see, let's imagine we go around this circulation direction of this loop. We're going to have E1 positive minus I1 R1. Then we're going to put R3 for simplification, which is negative 2. And then minus epsilon 2. And sorry, here I put it plus, but it's minus because we're going from positive to negative. What we observe is that this equation is no other thing than the addition of these two equations. We have epsilon 1, I1 R1, then these two cancel with each other, then I3 R3, and then epsilon 2. So this equation is redundant. In fact, what we notice is that whenever we have n loops, in this case we have 3 loops, so let's write it, n loops, this leads to n minus 1 independent equations. Similarly, whenever we have n junctions, this leads to n minus 1 independent equations. Now, once we have these 3 equations, which are the most that we can take and actually are the necessary ones to solve completely the system, to solve all the current values in terms of the quantities that are already given, what we have is that we would solve for I1 in terms of I2 and I3 in terms of I2, and then we would simply substitute them in this equation, which we would use as a backbone, and then you could find the values. However, that's a simple arithmetic and there's no point in doing it, mostly because we don't have values to plug in, and then we wouldn't know if we were right about the direction of the current, etc. So this solution is just simple arithmetic after this. Great, now let's see how we can group different elements. For example, we're going to do that with resistors. Imagine that we have a system, a circuit, with 2 resistors in series. Then we would like to find an equivalent system in which there is only 1 resistor, but the situation is completely analogous. That would be something like this. Now we would like to express this value of the resistance that is equivalent to these other two in terms of R1 and R2. To do so, we will use the second Kirchhoff law. We know that along this loop, the whole change has to go to 0. So if we have here the current and here the current, we're going to have, in this case, that E equals I R1 plus I R2. And for this system, we'd have that epsilon, sorry, not E, equals I R equivalent. Therefore, we observe that if in this expression we take the common product out, like that, we can identify that R1, R2 equals the R equivalent. Hence, we conclude that whenever we have resistors in series, we just add the resistance values and find the equivalent resistance of a single resistor put in their position. Now, let's imagine that our resistors are in parallel. Once again, we would like to simplify the situation so that we can substitute this part of the system by one resistor in a similar manner to what we did here. In this case, to solve this, we're going to use the first Kirchhoff law. We have here a first current, I, and then we have the current that goes over here, I1, and the current that goes over here, I2. In this other case, the current that goes over here is the same I. We know that I equals I1 plus I2. Moreover, we know that the change in voltage from this point to this point is the same than the change from voltage from this point to this point, and it's in fact equal to epsilon. Therefore, epsilon equals I1 R1 and equals I2 R2. Therefore, we can solve for I1 and I2 in terms of epsilon and r and substitute them in this expression. What that gives us is that I1 equals epsilon over R1 and I2 equals epsilon over R2. Moreover, we need to express epsilon as a function of this R equivalent. So we can substitute it here in terms of that I. From this expression, we find the simple solution that I, R equivalent, equals epsilon, which is equivalent to what we found there, and we have that I equals epsilon R equivalent. Therefore, what we get is that this expression gives the following: epsilon over R equivalent equals epsilon over R1 plus epsilon over R2. Therefore, by taking out the epsilons, which are a common product, and we can divide by them because we know it's non-zero or the circuit wouldn't be working, we will have that 1 over R equivalent equals 1 over R1 plus 1 over R2. And in that way, we have found how to combine resistors both when they are in series and when they are in parallel. That is all for today. I hope that you understood everything and you're starting to get a sense of how we can use these tools to simplify circuits and make our life much easier. Remember that if you have any doubt, you may ask them in the comment section and I try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel, press the bell and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome.